And now one more example from the projectile motion. This time we will ask about the velocity with which the projectile strikes the ground. Once again, we will have a projectile that is fired horizontally with a speed of 30 meters per second from the top of a cliff 80 meters high. So here is what we have seen so far. I have included the equations that we used for the projectile motion that helped us determine what the time of flight was, 4.04 seconds according to our previous examples, and the displacement in the horizontal direction, which turned out to be 121 meters. The question, of course, now is what is the velocity with which the projectile strikes the ground? Now, even though this is written in vector form, and it's one question, it's really two questions. Whenever we are trying to determine a vector, remember this problem is two-dimensional, so the vector will have two components, x and y. So in reality, this problem has two questions. What is the x component of the velocity, and what will be the y component of the velocity as the projectile strikes the ground? The x velocity, the x component, will be very easily found if you remember that there was one relationship here that pertained to the x, to the motion along the horizontal direction, that the velocity along the x never changed. I didn't deem it important enough to call it an equation, but it was there in our formula sheet. Vx will always be equal to Vx naught. So therefore, I can actually write that when the projectile is about to hit the ground, it is still drifting in the horizontal direction with a velocity equal to 30 meters per second. So the real question in this example is really, what is the y component of the velocity? So for the y component of the velocity, we can use equation 1, which is Vy is equal to Vy naught minus gt. So I will have that the y component of the velocity just before it hits the ground will be equal to the initial component, which was 0. Remember, the projectile was fired horizontally, minus 9.8 times the time that I actually determined in the previous two examples to be 4.04 seconds. So with that, I get for the y component of the velocity of the projectile to be minus 39.592 meters per second. Remember, minus indicates that the projectile now is traveling downwards, because all my equations 1, 2, and 3 are written with the implicit choice of up positive and down negative. Equation 3 can also give us the answer for the final velocity, and it's a good way to check our calculations and compare. If we have done everything correct, we should get the one and the same answer in two different ways. So let's check. Equation 3 is Vy squared has to be equal to Vy naught squared minus 2g delta y. My personal preference is always to go for the equations that rely on the given of the problem from the problem and not so much on previous calculations, simply for practical considerations. Sometimes we make numeric mistakes. So in equation 1 we needed our previous answer for the time. Equation 3 does not call for any previous calculations. So it's a much cleaner and more elegant way to get to the answer. So we're going to have Vy squared has to be equal to the initial velocity in the y direction, which was 0, minus 2 times 9.8, that was the value of g, times minus 80, which was the displacement given by the problem. So here, after I take square root of the product on the right, I see that the velocity along the y mathematically has to be either plus or minus 39.598 meters per second. Now, physically, I know the correct answer is going to be negative, and I'm going to take only the negative value as my answer for the y component. But I actually have a bigger problem. Compare with the value from equation 1. The answers actually differ in the last digit. So which one is correct? Is it 39.592 or 0.598? And if you can say, never mind, I'll just round to the 3 digits and I won't notice, it's still, there is some discrepancy, because one will, we can round to 39.59 in one case, or 39.560 to the other case. In any case, this is a good way. This is a good way to illustrate, for me to show you how important it is to keep track of the significant digits with which you write down your answers. In the previous examples, the time was the final answer in the problem, so in the end we just reported it with 3 significant digits, which is the standard way for many physics textbooks. But if we have to go back, if you go back, you will see that the time of flight was really 4.0406, and there's some more digits too, but just adding 2 extra digits here to the value that I used to calculate the y component of the velocity gives me a new value that is minus 39.598 meters per second, which agrees completely with the value from the solution through equation 3. So I wanted, this is, you might think it's minor, especially if you round those values to 3 significant digits, and they will round to 39.6 in both cases. But before we round and sweep everything under the carpet, I wanted to again show you how important it is to be mindful of those digits. If something is your final answer, yes, you can report with 3 significant digits or as many as your professor wants. But if you are going to use that value later down the solutions, you better keep extra digits. So there's the big lesson here: keep more significant figures if you're going to use your previous calculations. So what's left here is just to write the answer. We have determined that the x component of the final velocity is going to be 30 meters per second, and the y component is going to be minus 39.6 meters per second. Let me mark here the y component on our diagram here. But what if you're solving a problem in which you're explicitly asked to find the magnitude and the direction of that vector? Remember, vectors can be reported in 2 ways: components or magnitude and direction. So if you need the magnitude, you're going to use the Pythagoras theorem, square root of the sum of the squares of the components, which will give you 49.7 meters per second. And that is physically more intuitive to us, because all this splitting into components is a very mathematical and artificial way for us to analyze the motion. But in the end of the day, if you're observing that projectile, you're seeing that 49.7 meters per second. That's the velocity with which the projectile is striking the ground. And of course, you have to give the angle at which it strikes. So remember, the ratio between the y and the x components will give you the angle, well, will be the tangent of the angle with respect to the x-axis or to the horizontal. And so in our case, that will be 52.85 degrees.